So now we will be discussing about the CMOS fabrication, and as we know, CMOS stands for complementary metal oxide semiconductor, and the fabrication process or process flow we say. Okay, how we fabricate this, that we will be studying. Before that, I just want to show here how actually we are you may have a question like what is actually complementary metal oxide semiconductor. Complementary means here it is designed by using both N type and P type MOSFETs. Okay, so in general we draw, let me draw here. I'll show how the complementary metal oxide semiconductor is actually looks like. Okay, I'll just show you here such that, okay. Okay, sorry. Okay, I'll just show here. This is PMOS, right? This is PMOS and this is NMOS, correct? And here I have VDD. Okay, this is said as VDD. This is said as VDD, and this is grounded. We draw ground something like this. We say it is GND. GND, and this is our input V in, V in, and this is our output V out. Okay, this is V out, and the fourth terminal we shorted with the source for both the transistors. If you can observe here, see. So this is something like the PMOS, which is also said as a pull-up transistor, and this is NMOS, which is also said as pull-down transistor. Okay, so here the complementary metal oxide is the formation of both PMOS and the NMOS. This something it looks like this. Okay, because a simple MOS fabrication is different from the CMOS fabrication. So that is why I'm just saying you, I'll be discussing about the CMOS fabrication. So here this includes, yes, this includes the P well and N well and also twin top, and there are few technologies and there are few process integration approaches, that is bulk as well as the silicon on insulator. Okay, these are two approaches where we can either fabricate it on the bulk MOSFET, bulk, or either on a silicon on insulator. So what I do, the first first, the fabrication steps involves a series of photolithography techniques and chemical process and oxidation of silicon, then diffusion of impurities into the silicon, and deposition and etching of the aluminium polysilicon on the silicon to provide interface. Means what we are trying to do here is, first we will take a substrate, and on that we will be what we will be providing a well. Okay, either it might be a P well or N well, and later we use some techniques like such as a photolithography process technique, and then we use some chemical process where it involves oxidation, and in this oxidation is mainly used to coat the mainly used for the silicon dioxide protective coating for the device, and later we add some impurities with the help of the diffusion process, and then again yes, diffusion means adding impurities, adding impurity dopants to the silicon substrate, and therefore again we use either aluminum or polysilicon for the mainly this polysilicon is mainly used for the interconnection in the for the various circuits, means while designing a circuit, if I want to interconnect, or if I want to provide some interface or interconnect, then in that case I'll be using a polysilicon. So this polysilicon is now acting as a metal, and the silicon dioxide is now acting as an oxide, and semiconductor is now acting as a substrate. Either it can be a P or N, right? In this what we study, like as we said you, like the how the moss structure it actually looks, right? So it has a lightly doped substrate on silicon, where we say two islands, okay, that is diffusion regions, either it called as source and drain. That means it shows something like this, right? It is a substrate, right? This is a substrate, and above that I have an oxide layer, and above that I have a polysilicon layer, right? And then I have a two islands, that is a two diffusion islands. Actually we draw in this way, okay. So two two diffusion islands for source and drain, okay. So this is how we simply show a metal, oxide and semiconductor, okay. And then between these two regions a thin insulating layer of silicon dioxide is formed on top of this, right? Between this thin layer of silicon dioxide, SiO2, SiO2, okay, thin layer of silicon dioxide is grown on top of the semiconductor material, okay. And then on top of this a conducting material made of polysilicon. This is polysilicon, or we either a polysilicon or a metal gate is deposited on this. So metal, oxide and semiconductor, this is how it forms a MOS. The structure consists of N-type, yes, in which P device may be formed by suitable masking and diffusion. In order to accommodate N-type devices, a deep P well is diffused into the N-type substrate as shown. Okay, this is how this is actually happening, that we will look into the further slides. Okay, so in order to design a P well fabrication, a P well in a Cmos fabrication, we required various types of masks, okay. Like we have here, it is represent from mask 1 to mask 8. There are various maskings, means where where we will be using this mask 1, mask 2, that we will look into once we study about this fabrication process, okay. So what it here a simple yes, before this, before I talk about this the fabrication process, one thing should be sorry, one thing should be important, one should understand about how actually this substrate is actually forming, that we need to understand. So this is how is happening, like we say it is a wafer fabrication, right? In this wafer fabrication, we will have a furnace. Okay, a purified silicon is held in a molten state for about 1500 degrees centigrade. That means a purified silicon is now means it is a liquid form, and now it is heated. No, it is in the solid state, and now it is getting heated, putting it into the furnace and of around 1500 degrees centigrade temperature. In that temperature, it is getting heated, and a seed crystal is slowly drawn. A seed crystal is slowly withdrawn after bringing in contact with the molten silicon. That means what we are doing here is actually this, how this substrate is actually forming, that we are studying, right? In general, silicon, in the silicon which is available in nature, which is actually it is available in nature, and that is not used for the fabrication. Before it comes to the fabrication, it has been uh, very sensitively, it has been cleaned. Okay, and after that it has been made into the substrate, means we say it is a silicon crystal. Okay, we say silicon crystal. That means this silicon is now taking the shape of the crystal. Okay, so how it is happening? First, we took a molten silicon, I mean purified silicon, that is held into the molten state of about 1500 degrees centigrade, and then a seed crystal is slowly withdrawn. Means a furnace you have, in that a seed crystal is now withdrawn, and this will now come into the contact with the molten silicon, and slowly uh, I mean after the withdrawn of this seed, we say it is a ingot. Okay, several what you call several centimeters long, that is of 8 to what you call 6 to 7 I mean the length is something of around 6 to 8 centimeter, and the diameter of that will be around 8 to 10 centimeter. Okay, that means once we put into the furnace, and we slowly what you call remove, rather withdraw. Okay, we slowly withdraw that ingot, and therefore that silicon will now take the shape of that ingot. So therefore then what it does, it is now a dopant has been because here we need to dope, right? Here we are supposed to dope it. Dope it means we need to now add the impurities. Either it can be a P type or N type, because as of now we have created a substrate, right? This is now we are saying like the substrate formation, okay, or wafer fabrication we say. Okay, so as we are forming a fabrication for the wafer, therefore we are supposed to now add some impurities in that. So in order to add some impurities, we will now provide a wafer gas. Okay, sorry, it is a dopant gas, sorry. We will now means it is a crucible, and there we have what you call liquid melted silicon, which is heating up to 1500 degrees centigrade, and then we introduce the ingot into that, and slowly we withdraw it. Therefore that silicon material will now take the shape of the ingot, and then we and for this we will what you call, we will now provide impurities to that silicon substrate. So in this case, when we are adding dopants to that, here it will have, we can either to I mean make it in the two form, sorry, yes, dopants will add it, and then we will do the oxidation process. This oxidation process can be either we will put some silicon dioxide things. Okay, when we use this, we say it is a dry oxidation, and if I'm using a water vapor, means in the two ways we can do the oxidation process, either by silicon dioxide or else with the wafer, or sorry, or else with the water vapor. So now after forming, it is now the silicon is now sliced. Okay, and that slice is nothing but a silicon crystal where we will use it as a substrate. Okay, where we will use it as a substrate. So now this substrate formation, as of now we made it. Till now we have discussed about how this substrate is actually forming. Okay, later what I did, I have completely, I have grown silicon dioxide. Okay, in order to what you call, in order to introduce a P well into that, first I totally covered this with a silicon dioxide layer, and then what I do, I provide a photoresist and then I'll do a masking one. Therefore, at that particular area, this will get, this will be removed. Means that will be etched off. Okay, that will be etched off, and therefore now I introduce a P well inside this. Where this P well is now a P-type dopants are now introduced in this. As I have here a N-type dopants and here I have a P-type dopants. It can also, it can, you can interchange this. This can be a P-type substrate and this can be a N-type substrate, no matter what. Okay. So what I did, I took a substrate which is of N-type dopants I have already introduced with the basic steps, either with the I used some oxidation process there, and I introduced a dopant gas, and then I made it a, and then I have given impurities to this substrate. And later what I did, I have covered a protective coating. Okay, that is with the help of silicon dioxide, and then after that I just want to make this area, I want to make this a well. Therefore, in order to make this well, I have introduced again a photoresist. Okay, I have introduced a photoresist, and through that I have passed a UV light such that where, in which area I want to etch, I want to remove that area, it is getting removed, where we say it is a etching process. And then I have doped with the P type. Now another part is again I need to strip off, means I should remove the next process, as it is not clear here. The next process is I will be stripping off this oxide layer. Okay, I'll be stripping off this oxide layer, and then now I introduce again, I'll grow a complete oxide layer. I'll grow a complete oxide layer, and again I'll do masking 2. Okay, mass 2 I'll be doing, and then wherever is not required this oxide, then that portion is getting etched off. Okay, then next, which it is where it is forming a thin oxide and polysilicon, means both the polysilicon as well as the what you call thin oxide is formed here. And then again I need to introduce what you call this dopants, right? P type, it is a N type, so I'll be using here P type, and I'll be taking P type here for the body, right? This is used for the source and drain, and if I introduce here a P type, then it will be used for the body terminal. So in the same case here also, I'll take again what you call sorry. So this is how we are using. First, we use the lithography. In general, the Cmos fabrication steps consist of, as I said you, we are starting with a blank wafer, right? And then we are building up a inverter from the bottom to top, bottom up approach. That means we are taking from the substrate and then we are growing it all the layers okay. And then the first step here, we the first step here, the formation was like P, right? And then cover wafer with the protective layer of SiO2, that is oxide layer, and then remove layer with where N well or sorry, where the P well need to be built. Okay, remove the layer where N well should be built. Okay, if I say, sorry, if I say N well, it has to be P well actually. Okay, remove the layer where P well should be built. Okay, and implant or whatever, implant or diffuse. Okay, dopants into the exposed wafer. That means introducing dopants, okay, in the exposed area. That is, we say implantation. Okay, and then we'll strip off the SiO2. Okay, this is how we said about the process. Okay, first, as I said you, like in order to provide this envelope, we use some photoresist, and we say like photoresist, it is a light sensitivity organic polymer, and then it will softens that, and then where which is exposed to light, therefore it will get removed. Okay, so that was that. Then the next process was the photolithography. Means this actually, the N well that has been formed here was actually done with the help of a photolithography, where we exposes a photoresist through P well masking. Okay, we use a photoresist, means we are exposing a photoresist, that is this, we are exposing this photoresist through P well masking, and again we will strip off, means in the previous thing, and again we'll strip off this photoresist, and then we do etching. Okay, after stripping off we do etching, and this etching, uh, we in this etching either etch oxide with hydrofluoric acid, and that means it seeps through skin, and that means what, like only attacks oxide which resist has been exposed. That means what, it will only remove the SiO2. Okay, it will not that means what, it will not uh, it will not affect the surface of the substrate. Okay, that is about the etching process. And then for every process after the masking, whatever we do, we were doing a stripping of either the SiO2 or stripping of the photoresist. Okay, and then the formation of P well, what we do, we used a P well is formed with a diffusion or ion implantation. This, whatever the P well we actually formed it, this is actually I mean means it is actually formed with the help of a diffusion or ion implantation. So diffusion is nothing but placing a wafer in the furnace and introducing some p-type material, some boron gas, a p-type, because for the p-type I use a boron, for the n-type I use some arsenic or the phosphorus. So in order to make it diffusion for the p, place wafer, means we are trying to place this complete wafer in furnace with a boron gas, and then heat until as atoms diffuse into exposed Si. That means what, we are trying to when we are putting this, we are introducing some boron gas, and then we will heat it up until all the atoms will get diffused into the exposed silicon, because this was the exposed silicon, right? This was completely coated and this was completely protected, but this was the exposed, and therefore we are now introducing a boron particles or boron things into this, and then we do ion implantation. Then how this ion implantation is actually done is like a blast wafer with a beam of boron ions, and then these ions are blocked by SiO2. Rather, means it will not allow this ion blocks, or whatever these ion blocks are actually here, this will not means this will not allow to move still down. Okay, so this is about the ion implantation and the diffusion. And then polysilicon, as we know, polysilicon is now forming as an interface for the different layers in the circuit. And we do a chemical vapor deposition of a silicon layer, that is place wafer in the furnace with the silicon gas, or form many small crystals called polysilicon, and heavily doped to be, if I doped it heavily, then it will actually act as a conductor. So this polysilicon, whatever we use a polysilicon or a metal, this is actually used for a good conductor. And then polysilicon patterning. This polysilicon patterning will be actually done only here and here, because only two possible only in two parts we have, so it will actually done only here and here. Okay. So then I'll be using here a mask 3, uh, like a formation of pattern polysilicon nitride on a thin oxide region, and then this requires a mask 3. Okay. Then in a self-aligned process, we use actually oxide and the masking to expose where P plus dopant should be diffused or implant, P or N type, wherever. Because in this I use a P type, and here I use a P type body, but for this, and in this I only use a N type, and here I use a N type body, like that, either a P or N dopants. And N diffusion forms N MOSFET source drain, N well contacts, like that. So if I'm taking a P well things, if I'm using a P well here, then P diffusion is formed in the PMOS, like source drain, right? This is a source, or this is drain. These both can be interchanged again, and in a P well context. And this formation of diffusion or P diffusion, whatever we are doing here, is done with the help of a P plus masking. Okay, P plus masking, that will actually use a mask 4. Okay, this self-aligned means here, this one. Okay, then later we do N plus diffusion, and then we use a P-type diffusion. Again, we use a mask. Here, the mask we use here, like mask 5 and mask 6. Okay, and finally we provide some contacts to this. All we do final is like we provide masking. Okay, finally we provide some masking here. Contacts, sorry, we provide some contacts there, and this contact provision, we say it is a metallization. And then here we use a mask 7 as an in this, the whole chip, whatever, now this can be said as an a chip. Okay, so the whole chip is then has a metal deposited over it, surface in the thickness of 1 micrometer. That means a metal, we provide here a metallization, and which is having a surface of thickness of 1 micrometer, and the metal layer is then patterned by the photolithography process. This metal layer, whatever is now drawing here, that is actually patterned by photolithography, and this interconnection pattern uses mask 7. Okay, because initially we discussed about how these masks are actually used, that we have discussed, right? So now another part is like over glassing. Over glassing is nothing but we use some protective packing of that IC. Okay, we use a over glassing, and as I earlier discussed, like it is mainly we have used two we have two approaches. One is bulk approach, another one is silicon on insulator. So this we say it is a bulk approach because it is a silicon substrate, and from the bottom to up we were drawing it, means we were actually fabricating it. Okay, like I've introduced a P-well, then by mask 2 I have used a photoresist, then I have created a diffusion blocks here, and then I diffused here with a P and here with N, then I used mask 3, and later again I've stripped off the oxide. Like these are various steps, and I use some photolithography process in to introduce this. Those all things we have done. So as of now, what we are doing, we used all this process. But for a silicon on insulator, we say SOI, we say it is a SOI technology or SOI technique, and this is mainly used. The Intel is now, both are having a similar advantages, but the Intel is using a bulk technology and IBM is using a SOI technology. But if I want to show how actually this is, how it can be done is like, suppose it is a, I'm growing SiO2. This is SiO2 first. I'll write SiO2. Okay, silicon on insulator. So now this SiO2 is now acting as an insulator. Okay, and this is my bulk. Okay, this is my bulk substrate, or rather I say bulk substrate. I write it here as a substrate. This is my substrate. SUB. I simply write it in the short form SUB. And now this complete portion will be this. But the only thing is it is just placed above the SiO2. That is an insulator. So that is why the complete silicon, the silicon on insulator. Okay, that is why it is said as SOI, SOI technique. Okay, SOI technique. And one more point here is like we say it is a unipolar device. Why we say it is a unipolar device? See, as we say it has a two different types of enhancement. We have two types of MOS transistor, that is enhancement and the depletion, right? Coming to the enhancement, there is no formation of channel unless and until we apply some voltage source, then only the channel is created, and then the movement of electron is happening, and then the current generates inside the device. But in the depletion region, there is nothing like that. In by default, you have a depletion layer in that. Even though if I want to switch off this depletion layer MOSFET, depletion MOSFET, then I give some negative voltage to make it off. But in the case of enhancement MOSFET, even if I do not apply any voltage, we say the device is off. Okay, therefore as it is forming a channel there, okay, it is getting inverted. Okay, the channel is now getting inverted if I'm talking about a NMOS. So this is how we say, how we differentiate the NMOS and the PMOS. And specifically unipolar, because only if it is in the PMOS, only if it is in the PMOS, what is the channel? The channel is for the N, for the PMOS, the channel is something holes we have, right? And for the N type we have electrons. So only a single, either electrons or holes are now, what it is happening, it is getting controlled. Okay, only unipolar means only either one, any one it is getting controlled. So that is why it is said as a unipolar device. Okay, so thank you. Here I'll end up this session. So welcome back. Till now we have studied about the P-well CMOS process flow or fabrication steps, right? like these fabrication steps was included like having oxidation, masking, wet and dry etching, and photolithography, then diffusion process. Then after that we have seen how we dope, the doping things, how we have done, and at what temperature we were heating up. And after that we have also studied the contacts, the metallization, the process, right, the fabrication steps that we have seen. And next we studied about the P-well CMOS process integration, right? But now the question is for you people that how can we design a N-well CMOS, right? Here I want to show, here we want to discuss and we want to observe that N-well, right? N-well, right? N-well CMOS fabrication. Okay. CMOS fabrication, or I can say like process flow, right? We can say simply like it is a process flow. Okay, right? So what I do, I'll just give you 60 seconds. Just think of it. How can we design or how can we have a final approach of the N-well CMOS process integration, right? So your time starts and now you can continue. Yes. So, welcome back. So now we will just see how it is designed or how it can be fabricated by using an N-well. Okay, as we know, CMOS is the combination of both PMOS and NMOS, right? So here what I sorry. So here what I do is let me draw a substrate. Okay, assume that this is a complete. Just a minute. Okay, right? Let me draw a substrate. So here I'm introducing N well. I'm introducing a N well into the substrate, right? I'm introducing an N well. I don't know, this pen is moving up and down, right? Uh, Assume like this is P, this is N, sorry, right? Assume that this is N, right? This I'm drawing with the, yes, this is N substrate. Okay, let me write as N sub. Okay, let me write as N sub, and so assume these both are shorted, this one and this one, right? And as we know, this is P sub, right? This is P substrate, and here I have introduced a N well, and here, okay, right? And between this you have an oxide, right? And on top of that we'll be having a gate, right? The same here. Here it is a oxide, okay? Here it is a oxide, and on top of that I have a gate. It seems to be a bit small, but both are of the equal size. And this is assume this is both are drains, okay? Drain and drain. So this is V out, right? And as these both are gate, this is said as V in. Okay, this is oxide. This completely is oxide. Sorry. Yes, this is completely oxide, this part. And here this is also an oxide, right? Now I have defined V in and V out, and assume this is VSS and this is VDD. That means these are source, this is source terminal, and this is body terminal where both are shorted. And same here, this is source terminal and this is body terminal. That means this from here to here, this is now acting as a this is now acting as an NMOS, right? And this will sorry, I'm so sorry, and now this will act as a PMOS. Okay, so this is VSS source. Again, these are gates. These are gate. Okay, these are gate where both the general how we design, how we draw a MOSFET. We simply draw something like this, right? Oh, sorry. Yeah. let me draw. Yes, yes, it is visible, right? This is something. This is VSS and this is VDD, right? This is drain. This is drain, and this is your V out, and this is your this is your V. Sorry, this is your PMOS, right? The symbol of the PMOS is this, and later I'm putting this body terminal shorted to this, as this is source, right? And this is also source, right? I'm shorting this body terminal here, right? So this is something V in. So depending based on this, I have designed this, right? These are sorry, N plus, N plus, NPN, and this is P plus. This will be P plus, and again this will be N. Okay, because this is body, right? And this is here P. Fine. So this is how we define P N well CMOS process flow, right? So that it is very simple that we have introduced N N substrate into the P substrate, and then here defining our PMOS, and then this I am defining my NMOS. Okay, thank you.